Okay, good morning, everybody. My name is Jonathan Scott. I'm from the ESA European Astronaut Center in Cologne in Germany. I'll be the moderator for this session. This is a Microgravity and Physical Adaptation Session 1, ground-based, so if you're not expecting that, then you are in the wrong room. So we will have 4 speakers today, covering 4 different areas of physiology and the use of analogues to understand adaptation of human beings to prolonged gravitational unloading. So yeah, we'll have 4 presentations, around about 10 minutes each, and then a panel discussion. If it's okay, we will keep questions until the panel discussion itself. So if you have questions for individual speakers, please remember them for the end, and then we will put those questions all together. So with that, I'd like to invite our first speaker, which is Anne Pavé-Letron, from who's the Deputy Medical Manager of MEDES in Toulouse in France, and also Associate Professor of Neurology at the University Hospital in Toulouse, France. So with that, over to you.
Thank you. So thank you to ESA for inviting me to give the presentation. So I have chosen to speak about a quite specific subject, which is the neuro-ophthalmological changes in simulating microgravity with a focus on dry immersion. As you can see, many investigators participated in these studies, and I would like particularly to thank my colleague ophthalmologist, Professor Soler and Dr. Varenne. So as you probably all know, some astronauts may present after long duration flights some ocular disorders called SANS. And the latest definition is written here, is characterized by one of the following signs in 1 or 2 eyes, the presence of optic disc edema, which can be seen on the eye fundus, but can be also detected early by measuring the thickness of the retina by OCT. It's also characterized by changes in refraction with decrease in near visual acuity, globe flattening, and also other modification at the eye fundus. So here I will speak about the dry immersion model. You know that dry immersion is characterized by physical inactivity, changes in hydrostatic pressure with centralization of body fluid, also support and loading, and dry immersion induces quickly the main modification we have during space flight. And our objectives were to assess the effect on dry immersion on eye and also on cerebral circulation. So it was performed doing 3 dry immersion experiments. The first one promoted by CNES, in which we also tested the effect of countermeasure, tie cuffs, and the 2 other ones were promoted by ESA. Many investigators were involved in this experiment in order to provide a comprehensive assessment of the physiological response to this, I would say, quite new model, both in women and in men. So the question was, is the dry immersion able to induce some significant neuro-ophthalmological changes similar to SANS? So the measurement was performed with OCT, optical coherence tomography, to look at the retina. Before and the first day and the recovery, we did not observe a significant clinical optic disc edema, but nevertheless, we found small changes as an increase in the peripapillary retina nerve fiber layer, as in SANS, but also with only a little increase. We also looked at the changes in ONSD optic nerve sheath diameter. It's measured by ultrasound behind the eye, and this measurement is an indirect marker of changes in intracorneal pressure. And as you can see here, dry immersion induces a significant increase in ONSD during dry immersion, with partial recovery on the first day after dry immersion, both in men and women, with a larger intervariability in women. We also measure the intraocular pressure before and after, and there was no change in intraocular pressure. So, as I told you, one aim of the experiment was also to assess the effect of tie cuffs as a countermeasure to limit the thoracocephalic fluid shift. So the volunteers used this tie cuff 10 hours per day during the day. And you can see here, we look at the changes in ONSD. You can see that we again observed an increase in ONSD as a marker of ICP. There was a tendency to limit these changes with cuff. It was not significant. And we didn't find changes in intraocular pressure. But again, we find with using OCT a small increase in the retinal nerve fiber layer, with no effect on the tie cuff. We also studied during dry immersion the cerebral autoregulation. Cerebral autoregulation is the capacity of, is the ability of the cerebral to maintain a persistent and constant cerebral blood flow despite changes in blood pressure. So it's measured using continuous measurement of blood pressure with this small device, you can see, and measuring cerebral blood flow by transcranial Doppler. And as you can see here, we found that cerebral autoregulation was improved after dry immersion without significant effect of gender. It was the same in men and women. And what is also interesting, we look at the same time at the changes in ONSD, and you can see here that there is a large inter-individual variability in ONSD, especially during the recovery period. And we found that people who recovered, people with the increased ONSD, the increase in ONSD has a negative effect on the recovery of cerebral autoregulation. We also organized this particular experiment in which we looked at the dry immersion on a regional cerebral blood flow by using SPECT. SPECT is a single photo emission computed tomography with a radio tracer. And the advantage of this technique is that the volunteers were injected with the radiopharmaceutical where they were in the bath. And even if the images are acquired few hours later in the Department of Nuclear Medicine, it gives you the images of what happened when they were injected in the bath. And what we observed is that dry immersion induces a significant decrease in several cortical and subcortical regions, especially basal ganglia and bilateral occipital region, bilateral insula, and also temporal lobe, with no significance of thigh cuff. As you know, of course, if we compare to what happens with head-down tilt, you know that with gravity, ICP increase, there is a positional increase in ICP with the head-down tilt. It has been measured invasively with sensor in the brain. It also can measure indirectly by ONSD, so in acute head-down tilt. We also looked at what happened in prolonged head-on bed rest. Here, a 60-day head-on bed rest with two groups, with or without a countermeasure, which was antioxidant cocktail. As you can see here, the increase in ONSD was significant later during the head-on bed rest than in dry immersion, but we didn't look at what happens the very first day. There is a tend to decrease in intraocular pressure, and with this, during this long-term bed rest, after the long bed rest, two subjects had a significant optic disc edema. Many studies have been performed also of head-on bed rest. I will not present on the literature of the subject. Just you can see here that probably so head-on bed rest, prolonged head-on bed rest, induce significant changes, which can be similar to sense. There is a time factor, it increases time, and the most significant changes were observed after a strict head-on bed rest. So, to conclude, dry immersion induces a modest increase in intraocular pressure due to the fluid shift. Dry immersion also induces some very small changes in OCT. It's not clinically relevant, but it has been confirmed in long-duration experiment, for example, 10 days, as it's already planned. You can see that, for example, ONSD, changes in ONSD and OCT are significant, but after long duration of head-on bed rest. So there is really a need to compare these two models in order to have a precise idea of the kinetics of these changes. Of course, we have also to compare these changes with what happens to flight. And further investigation are needed to better understand what happens in a regional cerebral blood flow. And I would like to underline that this ground simulation allows us to perform this kind of sophisticated measure, I expect, in order to go further into the mechanism and to assess what happens during simulated microgravity. So I would like to thank all my colleagues in Toulouse, but also Marc-Antoine and Astia from Angers team, Rebecca and Marie-Pierre from MEDES, and all MEDES staff, and also all the volunteers who participated to these studies. And thank you for your attention.
Okay, thank you very much, Anne. Next on stage, we have Professor Jörn Rittweger. If you don't know Jörn already, he's from the German Aerospace Center in Cologne in Germany, the Department of Pediatrics and Adolescent Medicine. And he will talk to you about plyometric exercise training for space, which is a relatively novel form of exercise that we don't currently use on the International Space Station, but has some potentially very significant benefits over and above what we already get from our exercise on ISS. So thank you, Jörn.
Thanks, John, for not only the invitation, Ines, and also for the kind introduction. I'm really happy to be here today and present your results where we can say we have something that we can use for space. And these results have been obtained in Europe. So the departing point is that the countermeasures, as John alluded to already, that we have on board the ISS are not sufficient to safeguard muscle and bone. So this is a comparison in around about 16 or so crew members, mostly Russians, cosmonauts. And you can see here the red line is space, so this is days after immobilization, days after space flight, and the red line is below the two green lines, which is bed rest. So 6 months of ISS sojourn with countermeasure exercise is worse for your muscles than 2 months bed rest without exercise. So we're not there yet. And in bed rest, we have the solution, which is plyometric exercise. But I would like first to indulge a little bit into what are the regulators of bone metabolism and how do muscles adapt. For the bone, I think most researchers would agree with a scheme that is similar to this one. This is the famous mechanostat defined by Harold Frost. And what he claimed is that bones are able to adapt to their size and their structure to the largest forces they see every 1, 2, or 3 days. So it's the forces and the signal that governs the bone cell adaptation is the strain. So that's the unitless deformation that the cells see. For the muscle, it's a bit more complicated. Most muscle researchers would agree that, for hypertrophy and also countermeasure effectiveness against muscle wasting, you do need a mechanical signal. There are a plethora of candidates, focal adhesion kinase, filament C, other things integrated into the costomeres. The central hub for muscle adaptation is mTOR pathway, and it's effective by enhancing the muscle protein synthesis. And it's probably unlike bone, where only the peak stimuli matter. In the muscle, we also have an effect of the time under tension. So just one very short bout is not as effective as a prolonged bout. And we do have interference with metabolic factors. So most likely energy depletion of the energy-rich phosphates plays a role. They are funneled, these signals are funneled by the IMP protein kinase. And it's not so easy, really, to deplete your phosphocreatine. So sometimes, people say, I don't want to do a full weightlifting. I do something with lighter loads. But you really have to go to almost exhaustion. So it's actually more difficult to do this with lower loads than with larger loads. And then we obviously have interference with the dietary intake, foremost the protein intake. So we need to integrate the mechanical sensing and the metabolism, and that's why we typically load the muscles with high loads and go to near exhaustion. So if we first look at bone and ask ourselves which exercises actually provide the greatest strains, then we've done a study with optical segment tracking. It's a little bit invasive. You drill holes into the tibia, obviously after disinfection and anesthesia. And then we built up a biomechanics lab in the operation theater in 3 weekends and asked people to do something like 28 different exercises and looked at, where are the deformations in the tibia largest. And it turned out that it is the hopping either on one leg or on both legs. And the strains that we get are about 3 times larger as with static exercises. We also included squats with either just the body weight or 20 kilos on your shoulders or 40 kilos. If you then extrapolate how large would the load on your shoulders have to be until you reach the same deformation in the tibia as with the squatting, it was above 400 kilos. So that's not really feasible for most people. So we do have evidence that the plyometric exercises, hopping, one leg or two leg hopping, they really induce the largest bone strains. And if they induce large bone strains, there's reason to believe that it will also involve large muscular forces because it's the muscles that are the most important element in loading the bones. So this puts into question the so-called stretch shortening cycle. This is how many exercise physiologists would call the plyometric exercises. And the beauty of them is that our physiology, nature-wise, is optimally set up in order to do them. You can see this already from the reflexes. The short and, to some extent, even long latency reflexes, they really support these plyometric movements because they last typically 200 to 300 milliseconds. So that also means that plyometric exercises are a means of not only working on muscle, working on bone, but also reinforcing the reflex loops that you typically need in order for meaningful movement. And studies have suggested that what you get with these plyometric stretch shortening cycles is actually a force within the muscle that is larger than you would expect. If you look in the middle diagram at the gray strickled area, this is a force that is normally not explainable on grounds of the typical force velocity curve that a muscle would be able to develop. We have a force enhancement, and my belief is that we can explain this in very many ways, but the most important one will be the so-called residual force enhancement. This is a phenomenon that's long known. We don't know what really causes it, but if you stretch a muscle and then do a continued contraction, then you can actually elicit a larger force than you would have seen without that pre-stretch. So obviously, this also matters to muscle stiffness. Stiffness normally regarded as something negative, but stiffness is also positive when you want to go sprinting because the stiffness defines the resonant frequency of a mass spring system. So you need high stiffness really to be a good sprint runner. And when I do this kind of talk in geriatric clinics or with people working with older people, I convince them typically with the argument, have you ever seen one of your patients being light-footed? Because that does not, light-footedness is actually what means plyometric exercises. You stretch and release, elastic storage of energy and release. And so we see now in our collaborations with geriatric clinics that the inability to do hopping exercise is a very early hallmark of aging. I've spent the first 10 years of my scientific career to a great extent on vibration. So we have done one study with ultrasound, EEG, EMG, and so forth, where we demonstrate that vibration, whole body vibration, does elicit stretch shortening cycles in the human muscle and also elicits reflexes. We then used also a combination of resistive exercise with vibration in the Berlin bed rest study and found that it was 100% effective for the preservation of muscle strength. I would say also if we acknowledge that some fluid shifts do occur in the muscle, Dieter, you've analyzed the biopsies, our opinion was that it was very effective for safeguarding muscles in bed rest, and it was also fully effective to safeguard bone, the tibia bone in bed rest. And the second Berlin bed rest study actually demonstrated that there is a specific benefit in the vibration. So there was one group that did the resistive exercise only and one that combined it with the vibration. And you can see here the top curve in the diagram. That's the curve of the group that did the combination that was significantly higher than the group that did resistive exercise only. And we also know from this diagram that training only 3 times a week is not enough. In order to prevent muscle loss and bone loss, my opinion is, well, the data show at least 5 or 6 times is necessary. And then I would say the greatest benefits that we had with countermeasure exercise, or at least, the best documented benefits were with the so-called RSL system. This is a sledge system where you can jump in horizontal position. So it has almost constant force mechanism in it. It's a pneumatic system, and it was fully effective for the bone and actually even elicited an increase in jumping power, which is very difficult to come by even if you do resistive training or all other kinds of trainings. We work a lot with athletes. It's really difficult to increase your jumping power, and we did it in a bed rest study that used a jumping paradigm. So I think if you really want to be fully effective in spaceflight, you must include plyometrics. There can be trade-off for missions where you say we can compromise and have maybe reduced effectiveness, but my belief is that at least if you don't send 80-year-old people who can't hop and jump anyway, if they're reasonably young, you'll have to include the plyometrics. So we've been funded by, or we've been contracted by a company that was funded by ESA to develop 2 new countermeasure exercises. And one was athletic, which has the ability to do plyometrics. In the first round, it worked so-so, and we now have a master's project to improve its operability. So adding the plyometrics to the space has a lot of pros. We'll have full effectiveness for bone and for muscle. We also observed in both studies, the Berlin bed rest study and the RSL study, some effectiveness for the cardiovascular system. This is probably accounted for the high-intensity interval training elements that this kind of training has. You do a series of 12 hops, your heart really goes fast, and then you do another series. And we also see effects on the sensory motor systems. The cons are obviously the mass and energy budgets and the shock and isolation vibration, but clever engineers are able to cope with those. So also looking into the future, if we're on Moon and Mars, I believe that we can use gravity, what's left over of gravity there, 1/6 of a G or 40% of a G. We can use this in a clever way because the dynamics of a hop do not really depend on gravity. They mostly depend on your velocity. Because as you hop, you can produce 5 to 6 G under your feet. So it doesn't really matter whether you have a full G in addition to that or not. And that's been demonstrated here in a study, the MOLO study on a treadmill, where basically you see that the time of contact, which is on the y-axis, actually scales a little bit with the gravity, but that it's fairly independent of jump height. And that's all I have to say today, except the replies that I will give to your answers later.
Okay, thank you very much, Sean. Next on stage we have Marc-Antoine Costard. He is the Director of Clinical Research Centre at Angers Hospital and the President of the International Society of Gravitational Physiology. Today he will talk about a comparison of the cardiovascular responses to progressive low body negative pressure in men and women after 5 days using the dry immersion model. So Marc-Antoine, over to you.
Thank you very much. Thank you very much for ESA and the organizer to give us the opportunity to present some results and to discuss about the dry immersion model. So I would like to talk today more specifically about orthostatic intolerance and LBNP procedures. So it is known that there is a gender difference in orthostatic tolerance after space flight. So this is all results performed with shuttle flight experiment, and we have seen that women have lower orthostatic tolerance after short-term flight when they return to Earth. So there are many explanations for this gender difference in cardiovascular regulation. It could be related to venous pooling at the leg level, at the pelvis level. It could be also related to the regulation of the cardiovascular system, more related to heart rate increase or to vasoconstriction regulation, and it can be also due to difference in autonomic nervous system regulation. However, data with women and direct comparison between men and women for cardiovascular deconditioning are lacking. So this is one of the scope of the ESA Vivaldi program with the experiment Vivaldi 1 and Vivaldi 2. So the main goal of this program is to have a comprehensive study of the dry immersion model with 5 days of dry immersion, and also to have a comprehensive comparison of gender comparison concerning the deconditioning. So Anne already talked about the model of dry immersion. So this is a specific model that initially was set up by Russian medical teams to study effect of microgravity on ground. So this model induces enhanced physical inactivity, muscle atonia, unloading, and free shift. And it might be a better model than bed rest to induce free shift. At least it can be a faster model compared to bed rest. So for this presentation today, I would like to give you our first preliminary result concerning the LBNP test that were performed before dry immersion and just immediately after dry immersion. So this program were performed at MEDES. We had a 5 days dry immersion in women, 5 days dry immersion in men. So 18 women were included in Vivaldi 1, 19 men were included in Vivaldi 2. So it was rather young people, around 30 in both groups. We had only 17 data for women with dry immersion, as one woman had a very strong reaction during pre-LBNP test with a strong syncope. So we decided not to perform LBNP after dry immersion. So LBNP, for lower body negative pressure, it's a common test to evaluate orthostatic tolerance. So we induce free shift to stimulate the cardiovascular system, and we record how cardiovascular system responds until, if it happens, scene of presyncope or syncope. So for this experiment, we decided to do a progressive LBNP test, so we can evaluate in each step what's happening for the cardiovascular system. So it was 10 millimeter mercury steps of 3 minutes from 0 millimeter mercury, it's basal, until 60 millimeter mercury depression as maximum depression. We evaluated the duration of tolerance in minutes, the orthostatic tolerance index, it's this duration multiplied by the level of depression, and we also performed hemodynamic analysis using the model flow. So you can see in the picture the system of LBNP, and the subject had a device. It is a like FinaPress device, it's photoplethysmography, and we can measure continuously the blood pressure wave at the finger level. And there are mathematical models where we can analyze the blood flow, and by analyzing this blood flow, we can have some information on the hemodynamics, such as the stroke volume and the total peripheral resistance. So with this system, we can have for each step of the LBNP, of course, the blood pressure, the heart rate, but also stroke volume and total peripheral resistance. You have here the kind of result, raw result we can record on a bit-by-bit basis. You have the blood pressure, heart rate, stroke volume, cardiac output, total peripheral resistance. And you can see between the minute 25 and 30, decrease in blood pressure, a high increase of heart rate. So we decided to stop the test at that time, and it was a presyncope symptom, and we can have the time of tolerance. We can also, as you can see, for each level of depression, have an idea of blood pressure, heart rate, stroke volume, cardiac output, and total peripheral resistance. So concerning the results, first about the orthostatic tolerance time after dry immersion. So in orange it's for women, and in blue it's for men. So we can see that there is a little less orthostatic tolerance in women compared to men, but it was not statistically different. compared to what has been already published and to what we expected, finally, the difference between men and women for orthostatic tolerance after dry immersion is not so much as expected. At least it is not statistically different. To have a more precise index, we could use this orthostatic tolerance index, the same in orange women, in blue men. You can see the decrease of this orthostatic tolerance index before dry immersion and after dry immersion. And the same as for the duration. Orthostatic tolerance index are rather comparable between men and women. Before bed rest, you can see one man had a very low orthostatic tolerance index. We had to stop the test very early. It was not a strong syncope as in women, but you see, even before bed rest, the orthostatic tolerance could be impaired in some subjects. So to try to understand what's happening during bed rest, especially after dry immersion, so we draw changes in heart rate, stroke volume index, systolic blood pressure, diastolic blood pressure, and total peripheral resistance for each step of the LBNP, with all the subject that still remains with this step. So we are very surprised to see that for heart rate and also for stroke volume, changes appear strictly the same in men and women. So there is no such difference in cardiovascular regulation for heart rate and stroke volume in men and women. If you look at the diastolic blood pressure and the total peripheral resistance, it appears that in women it increased a little, so that is in favor of vasoconstriction, that appears greater than in men, even if it is not statistically different. To analyze LBNP, it's always difficult, and I think we usually under-analyze the result we get from LBNP. We mainly give the result for orthostatic tolerance, but it's more difficult to go exactly what's happening, mainly because not all subjects could go until the last step of LBNP. So that's why we would like to try to have a more individual approach and to look for individual responses and focus on individual specificities. And I'm not going to comment all the graphic, but just to show you that for each subject, the cardiovascular answer to LBNP before and after could be different. And in this graph, we can have several information. Is it linear changes or not linear changes? From which level of LBNP changes occurs? So I think we can have some more individual specificities that we can interpret to better understand orthostatic intolerance. So this was the result of heart rate in women. We had the same in men. We also do the same in stroke volume, and we were very surprised to see that the decrease of stroke volume with LBNP appears very linear before and after dry immersion, such as there is a linear relationship between fluid shift and stroke volume, and it's the same before and after a dry immersion. To go further, we also try to look for correlations. So first correlation we want is to establish links between changes in plasma volume and orthostatic tolerance. You have below of this slide the plasma volume changes during dry immersion. So we have a comparable hypovolemia, about 19 to 20% decrease in plasma volume in both groups. Plasma volume is an important parameter for orthostatic intolerance, and for sure it plays a role in orthostatic tolerance. But could we use plasma volume changes to predict which subject will have greater orthostatic intolerance? That's why we perform this correlation. So for the entire group, Vivaldi 1 and 2, there is no statistically correlation between orthostatic index and plasma volume. and it was the same for Vivaldi 1 and Vivaldi 2. So no evidence for significant statistical correlation between orthostatic tolerance after dry immersion and changes in plasma volume. We have done the same with body mass index. For all the group, there is a correlation between body mass index and tolerance, and it's more evident in men, it was Vivaldi 2, than in women. So we have seen a correlation with body mass index in men. Body height, it's also known that body height is an important parameter to determine orthostatic tolerance. So we do this correlation. Globally, there is no statistical difference. However, in women, we observed a correlation between height and orthostatic tolerance. We have done the same with the venous distensibility at the calf level, as venous pooling also is an important parameter for cardiovascular regulation in standing position. We didn't see any correlation in both groups, but it appears that in men, this correlation is more evident than in women. So this is where we are now to the analysis of the LBNP data. So we'll continue the analysis, but I think it was important to show already these results and maybe to raise discussion. Just to place this result within the Vivaldi program. So the Vivaldi program is a very interesting program for us, as we will have two populations, almost 20 men and 20 women, where we can compare all the deconditionings. So it is not so often that you have such number of subjects in the same experiment. So with the expert group, we are working to get a global picture of men and women deconditioning with all the functional testing. So we work on this picture, and I hope in a few months it will be published, so we can see exactly where are the differences, if they are, between men and women deconditioning. So Vivaldi is a unique opportunity to compare direct orthostatic tolerance in men and women with a rather high number of subjects, and we are now prepared to Vivaldi 3, where we are going to compare head and bed rest to dry immersion. Orthostatic tolerance time and index are not statistically different in men and women with LBNP testing after 5 days of dry immersion. Heart rate truck volume during LBNP after dry immersion seems strictly the same in men and women. So now analysis at the individual level should be done, and a comprehensive correlation between parameters should be investigated further. So thank you very much for your attention, and I would like to thank particularly the ESA dry immersion expert group, who is very active, and in particular Nastia, who really do wonderful work to promote the dry immersion model, and MEDES, who implement this experiment. Thank you very much.
Okay, thank you, Marc-Antoine. Our final speaker today is Rodrigo Fernandez Gonzalo. Rodrigo is the senior researcher at the Karolinska Institute in the Division of Clinical Physiology and Department of Laboratory Medicine. Rodrigo will speak to you today about body composition during a very recent 60-day bed rest study that we have performed, specifically looking at a combination of exercise and artificial gravity. So a very unique kind of direction for bed rest research and potential countermeasures. Rodrigo, over to you.
Thank you very much, John, for the introduction. And thanks to the European Space Agency for organizing this workshop. I think this is the way we can talk to each other and advance our research further, and also for giving me the opportunity to present, of course. And as John said, I will talk about the bed rest study that was completed very recently. So I think the last subject was standing up from the bed like 4 months ago or something like that. So very recent bed rest study. And the results I will present are quite preliminary, but I think it will help to start understanding how the countermeasures that we tested actually impact the physiology of the human body. So very fast, because most of you know that the bed rest model is one of the gold standard models to simulate microgravity on Earth. The beauty of it is that it triggers systemic effects in the human body. And something that I would like to highlight is that I think a lot of people consider it a very good platform to first investigate the mechanism behind the alterations that we see in the different physiological systems, and also it's a very good platform to test new countermeasures. So, speaking about countermeasures, I don't know how many people are in this room, maybe I'll be positive, 200. So if I ask all of you for what countermeasure would you employ in the next bed rest study that ESA will have, I will probably have 201 different answers. So there are a lot of countermeasures that we can employ, from different types of exercise, resistant exercise, aerobic exercise, with all the array of possibilities that those modalities offer: whole body vibration, artificial gravity, nutritional aspects, ergogenic aids, different drugs, and along, etc. So the European Space Agency, several years ago, decided to focus on some of these countermeasures. And it was resistant exercise, aerobic exercise, artificial gravity, and whole body vibration. And they put together and they designed two parallel bed rest studies called BRACE and BRAVE. Beautiful names. BRAVE was a bit more beautiful than BRACE, but anyway, the first study, BRACE, is the one I will talk about, and BRACE stands for bed rest with artificial gravity and cycling exercise, and the BRAVE stands for bed rest with artificial gravity and vibration and resistant exercise. So let's have a look at the BRACE study. It was performed in MEDES recently, in Toulouse. It was 60 days, 6-degree head-down tilt bed rest, 24 male participants, and 3 groups with 8 subjects per group. I think there are some format issues with my presentation. Sorry for that. And then what did we do to those 24 subjects? There is a wide array of bed rest standard measures. And then we were 14 different research groups. You can imagine if you put together 14 researchers in a room, it's quite difficult to agree on anything. But this is one of the positive things I'm taking home from this project, is that the willing to collaborate and compromise things for the benefit of the entire group prevailed in most of the discussions, so I'm very happy I could take part of this exercise. When it comes to the different groups, as I said, the subjects were divided in 3 groups. The first group was the control group. From now on, the control group in my presentation will be displayed in red. So this group just stay in bed for 60 days. Then the next 8 subjects were randomized to the bed rest and cycling group. During my presentation, this group will be displayed as green in the figures we will see in a few seconds. And the third group was doing bed rest, cycling, and artificial gravity. And the color for this group will be blue. Okay? So let's have a look at how the countermeasures look like in this bed rest study. So the cycling group did 6 times a week using a 2-minute interval cycling exercise, horizontal cycling, with the load that you see on the screen. It's based on the maximum oxygen uptake. Let's say the starting point is 40% of that maximal endurance capacity, and then it has different steps to 65, 70%, up to 80%, and then the same steps on reverse order. And then the cycling and artificial gravity group did the same exercise, horizontal cycling, but on a short-arm human centrifuge, which is quite, it's quite difficult to imagine how to ride the bike while being rotating. And it's quite nice to see how technology, what technology can do for us. So the artificial gravity was not constant. It started at the orthostatic threshold, and that was predefined before the bed rest started, minus 0.15 Gs, and that it increases in 3 different steps until the 70% of the maximal artificial gravity capacity for that subject of tolerance was achieved, and then it decreased. So as you can see, there were 4 minutes where there was maximal artificial gravity and maximal cycling load. So this is the brace study. And now I will focus on some of the measurements that we did in the project I was lucky enough to lead, and this is detailed body composition. The project is called ESA-HRE, and it uses a more integrative approach to investigate the changes and how the countermeasures affect those changes induced by bed rest in the skeletal muscle and the immune system, with also a big component of cardiovascular and metabolic assessments. So for the detailed body composition analysis, we used MRI, magnetic resonance imaging, and we did it before and after bed rest. BDC stands, well, for baseline data collection, day 10, and then HDT 52. That means that was the day 52 that the subjects were in bed. Why 52 are not 60? Good question. The thing is that at HDT 54, these subjects were having a muscle biopsy, and since I was quite interested in the muscle volumes of the knee extensors, so here, and we take the biopsy from one of these muscles, we didn't want the muscle biopsy to impact our measurements in muscle volume. Because after the muscle biopsy, you have some inflammation, some fluid shift, and that can influence some of the measurements. The total scan time, and I think this is important because if you have ever worked with MRI, some sequences can last very long. This one takes less than 10 minutes, or around 10 minutes. And one condition was like the subjects had to stand on horizontal position at least 30 minutes before the scan to account for any fluid shift that may interact with the changes in the volumes and the compartments that we were measuring. Here in the image, you see a reconstruction of the detailed body composition analysis that is done by AMRA company. This is a reconstruction. We don't see the results like that. But on the right side of the picture, you see all the variables that we get through this analysis. So it's quite a detailed body composition analysis, right? So muscle volumes, fat infiltration, fat compartments, visceral fat. We have that for the anterior posterior thigh. We have that for the left and right leg. So quite detailed analysis. Now I will start with some results, preliminary results. For your information, since I'm talking about detailed body composition, you should know that these subjects in brace, they lost about 2-3 kilograms, and that was, there were no differences across groups. And I will start with the fat ratio, so how much fat in relation to the total body mass these subjects had. I used a mixed model analysis, and you can see the main effects and interactions in the small numbers. And the significant differences between groups is a French study, so I thought the croissant was a good symbol to indicate significant difference in this study. So when you see a croissant, means that the difference between those two groups is significant. And as you can see here, the control group in red actually increased the percentage of body fat if you compare it to the group that did cycling and artificial gravity. and the cycling group was somewhere in between. So we have the first indication that, well, the countermeasure seems to work, at least for this variable. Let's check the next one, which I think is a very interesting one. So the quadriceps fat-free muscle volume. So how much muscle we have in the knee extensors. As you know, these muscles are very important because they help us to move around, to sustain the posture. And with bed rest, we see a classical decrement. And these numbers, 50% decrease in quadriceps, is what we usually see in the duration of bed rest that we employed here. And here you can see, again, that the control group lost a lot of muscle. But you even see 2 croissants for the difference between the control group and the cycling and artificial gravity. So that 2 croissants meet a p-value lower than 0.001. So the countermeasure with artificial gravity actually had the major effect in muscle mass decrements induced by bed rest. And we see, once more, the green group, the cycling group, somewhat in the middle. Let's check another variable that I think is very important for muscle quality, very related to different types of musculoskeletal conditions like sarcopenia, cachexia, etc. So not only you lose muscle mass, but you actually have fat going inside your muscle. And that means your muscle quality decreases. That's how we put it forward. So here, we don't see any significant difference between groups. We see a main effect of time, meaning that during bed rest, the 3 groups, in this case, increased fat infiltration in the quadriceps muscle group. But if you look at the picture, there is one group that appears to to have a bit lower fat infiltration. And you have to remember, we only have 8 subjects per group. So the statistical power becomes a bit tricky in this case to assess small changes across groups. But still, same profile. Control group, cycling in the middle, cycling and artificial gravity to the other extreme. The last variable I will show you today is the abdominal subcutaneous adipose tissue. And again, we see the same pattern. There is no interaction, so we cannot talk about differences between groups. There is a main effect of time, indicating that the 3 groups, in this case, decreased subcutaneous adipose tissue. But look at the blue group. It seems to decrease a bit more. Again, non-statistical significance. We don't have interaction, so some statisticians would even kill me if I mention that. But please, remember, we only have 8 subjects per group. And sometimes in physiology, you have to be a bit flexible, at least in this type of presentations. Of course, as a reviewer, I would never accept that myself. But here, maybe we can discuss that a little bit and open the floor for discussion. Because maybe, I don't know, had we had 12 subjects per group, then I could have put some croissants in these pictures. Who knows? This was all. The conclusions that I would like you to take home is that bed rest, using the detailed body composition analysis that we do, you actually see how the muscle mass decreased, that there is an increase in fat ratio and in intramuscular fat content. That's, I think, quite novel here. And there is no change in abdominal subcutaneous adipose tissue. The countermeasures, remember the green in the middle. It seems that cycling works for these parameters to counteract the effects of bed rest. And if to the cycling you add artificial gravity, it seems it works a bit better. So what are the future directions? I'm very interested in diving into the data of the posterior thigh, so the hamstrings, because we have seen in different conditions affecting muscle, like children with cerebral palsy, multiple sclerosis, or stroke, that they show an increased fat infiltration. So I'm very keen in looking how bed rest affects this in the hamstrings muscle group. We have data about visceral fat, also about liver fat. So this will be quite interesting to have a look at it. And also to compare with the, you remember my third slide, with the other 60-day bed rest study that is currently ongoing right now. Right now, those subjects are in the recovery of the first campaign. Of the BRAVE, this was the BRAVE study, that they use resistant exercise and vibration with and without artificial gravity. And of course, as I said, the project I'm PI in this bed rest is more, uses a holistic approach. That word has appeared in this forum before. So to put everything together regarding metabolic data and also cardiorespiratory outcomes. And of course, this will be done in collaboration with some of these other 14 research groups that participated. Finally, I would like to thank my colleagues from KI, Eric, Tommy, and Mirko. They are helping me a lot, doing an outstanding job with data analysis. Then the MIVER RNA team that involves Slovene people, French people, and Swedish, Spanish people. And also, of course, the MEDES team that pulled off a tremendous, gigantic study, in particular, Rebecca Marie-Pierre. It was an amazing experience to be in MEDES. And finally, the fantastic, not 4, the fantastic 24 subjects that endure this bed rest study. Because if you think about it, this is probably the most aggressive intervention you can do in healthy humans and still get the approval from the ERB. So they were outstanding subjects. And of course, the people that are paying me to come here and to do the research I do, in particular, Rins Tirelsen, so the Swedish National Space Agency, KI, and of course, ESA. And with that, I'm done. Thank you very much.
Thank you, Rodrigo. If I could invite all of our speakers back up to the stage for a short panel discussion. So yeah, firstly, thank you very much for different topics, but all in similar platforms that we're currently using for analogs to understand what happens to astronauts in space. I wanted to start really looking at the future of these models. We've talked already about exploration-focused research. There are so many things we could investigate. Budgets will always be limited. 60-day bed rest study is kind of the model for this long-duration bed rest study. Obviously, these bed rest studies are expensive, logistically very challenging. There are people in the room who know this more than many. I wanted to ask all of you in your respective areas if you feel that a 60-day bed rest study is strictly necessary to detect the effects that you're looking at and potentially evaluate countermeasures that we might use. Do we need a full 60 days? Could we go down to maybe 30 days or 21 days, and as a result have more bed rest studies that we could investigate more things with the same budget? Maybe, Ewan, could I start with you and Bowen in particular?
Well, that's a very good question. We know that 90 days is not necessary, but that 60 days does the job for bone. For bone, I would argue that you need the 60 days. We correlated the data from the 90 days Toulouse bed rest study, 2001 and 2, and we had measurements after 60 days, after 28 days. So 28 days you could not predict either 90 days or 60 days. So for the bone, I think we need it. But of course, I realize, it's a big undertaking. I'm not so convinced that the main argument is really the money and the effort, because a 30-day bed rest study is not much more cheaper. So it's still difficult to find people. So, if you address only 80% of the questions with a 30% bed rest study, but it still costs 80% of the budget, I'd say, let's get all the answers that we want.
Okay. And in the area of SANS, this is obviously a relatively new condition compared to perhaps the things like musculoskeletal physiology, which we've been studying for a while. Do you think SANS is one of those topics that really evolves over such a period of time that 60 days is necessary to take those differences?
No, you see it after 20 days, 20, 30 days.
Yes, as I said, some really relevant changes similar to SANS observed in flight have been also reported after 30 days of strict head-on bed rest. Nevertheless, there was also some differences between what we observed in spaceflight and in bed rest. For example, corridor thickness is increased in spaceflight and not in bed rest. So I think head-on bed rest is a good model to induce SANS, but with probably some differences with what we observe in spaceflight. And I will be also very interested to what dry immersion will induce with a longer duration, because we already observe some very small but significant changes with only 5 days of dry immersion. So maybe we will observe also significant changes, more significant changes after 10 days.
And specifically on the topic of dry immersion and duration, how far can we push dry immersion in terms of duration? Is there I mean, obviously we're relatively short now. Do you have any feeling on how far we can go in terms of subject compliance and ethics and things like that?
I don't know, maybe I will let Marc-Antoine answer, but...
There were in Russia 21 day dry immersion, and when we discussed with our colleague, sometimes they say it's a little too long. So that's why with Vivaldi 3 we are going to implement 10 days dry immersion. So maybe between 5 days or 2 weeks, I think it's a good duration for dry immersion. So let's see what 10 days dry immersion we will give as result with Vivaldi 3, but we will answer to this question. And I think that dry immersion will be the opportunity to go again to short-term models. I agree with you that, John, that long experiments are important for long-term missions, but as now we are going to move with shorter missions, and maybe to be more reactive and to be able to test more hypotheses, we should also consider short-term models with bed rest or with immersion, and maybe early markers. For bones, I know that bone markers change after a few days, so maybe we can use these early markers to guess what will happening with the longer models.
Yeah, I think that's kind of leading on to, are there new measures we could take that would allow us to do that? Yeah.
Those bone markers would not have indicated the successfulness of the 2 successful studies that we did, long-term studies. So basically, you would have found, if you had I looked at those data, took the data from the 2 60-day studies, in the first days, there was no effect. So you can't replace the morphological measurement either by PQCT or MRI by markers for bone, and probably also not for muscle.
Yeah, Rodrigo, any thoughts?
Yeah,
study durations?
Yeah, answering your question about the utility of these models. If you ask me as a researcher, I would say yes, we need them, because it's a beautiful model to investigate the physiological changes. And also, the translation to the clinics, it's very close. If you ask me as ESA, I think the way to go is defining a question, because now researchers can choose the question we want to investigate. So if I were ESA, I would define, okay, this is the question we want to answer, and this is the duration of the mission, so let's try to make it as similar as possible. And then try to integrate as much, science, free science, as possible in that model. As it looks like, I totally agree with John. You should have the morphological changes, because so far with the biomarkers, we are not that close yet to be able to measure one thing and say, this person will lose 10% of muscle, 15% of bone. But it has to make sense with the agenda of ESA. And maybe I'm shooting myself in the foot as a researcher, but it makes sense.
And
sorry.
of course, head-on bed rest will be also necessary to evaluate the effect of countermeasure. So
yeah, moving on to the topic of the questions we should be answering. For each of you who've talked today about different topics here, bone, jumping, cardiovascular physiology, if you had to choose one particular subtopic within your topic that should be the focus of a future study, do you already have a feel for where that focus should be? And we talk about ESA directing exploration-focused research, but we're only really identifying areas that we feel are important. We're not telling people exactly how those areas should be addressed or which topics specifically should be tackled. So maybe start with you, Rodrigo. Do you have a feel of where is that one important question in your area that should be the focus of future analog studies?
So looking at the moon missions, I would say the focus would be how much can we allow an astronaut to lose muscle or bone without having consequences for his or her health and mission performance. And then based on that, okay, let's work on that and avoid that person to going above or below that threshold using different countermeasures. But I think to define this, how much can we afford to lose kind of thing, I think that would be a good way to then start working on all the other questions. Because right now, honestly, I don't see a point of having astronauts coming exactly with the same muscle mass as the one they go. Is that really necessary? They will not start playing a soccer match here after they arrive. So from a health perspective, yes, but for example, muscle can be recovered. Maybe bone, no. So maybe focus more on bone if they lose it in 30 days. So that type of questions, I think, will be quite interesting to predefine or have some idea about that.
Yeah, and that is a direction that we are heading. What is acceptable? If the goal is to preserve everything, I think it's an unrealistic goal and maybe unnecessary, but yes, it's preserving a sufficient amount of function that they can continue to do the jobs that they need to do, and then also when they're home, that the consequences are temporary and short term, and we don't induce any long-term changes. You're in the area of jumping. Obviously, we've done one bed rest study. We had a very specific protocol that was designed. Is there a change to that protocol or a different type of protocol that you might like to see in a future plyometric study that would maybe optimize those results that we got?
Well, I'd first agree with Rodrigo. I mean, second to those hypergravity studies that now are being done, Brave and Brace, which are great studies. Hypergravity is the next goal. And the question you addressed is one question, how much can they decondition? I'd say from an occupational health perspective, either from ESA or private space flight, it's not just about deconditioning, you need to keep the people healthy. About moderations to jumping, I think, as I ended with my talk, will lunar gravity be enough to allow us to do jumping exercises on the moon? So that we could do with the bed rest study. You could decondition people to different extent, and you got the lunar facility together with DLR, and drive them over from the NV hub and suspend them with different kinds of gravity, and then you see what they're capable of doing. That would be my dream study as a next frontier.
Okay, hello everyone. My name is Inês Antunes. I work for the European Space Agency. I'm a science coordinator. I'm also supporting the moderation with John. I do have a specific question because now, of course, artificial gravity is of interest. We have seen that today as well in the presentations. And it comes with benefits, but also with limitations, and especially if we want to fly artificial gravity. So if you can elaborate also on the limitations and the benefits, although some benefits were already mentioned by Rodrigo today, but also, do you think that the impact, the benefits are significant enough to justify even that effort, that investment for implementation in space? I saw that in Rodrigo's presentation, it really makes a lot of croissants, but yeah, could you elaborate on whether it is really significant, or even if we could think of other countermeasures that could compensate with artificial gravity being it so demanding.
I mean, if you visit one of these short-term human centrifuges, I don't imagine that flying anytime soon. And I know ESA has a lot of money and a lot of things, but
we
man,
don't.
I think you can come up with maybe a model for artificial gravity that is not rotating subjects, I don't know, using other type of instrumentation that I don't know yet, but or coming up with other countermeasures that have similar effects but are logistically easier to implement. Yeah. But for example, with the artificial gravity, when it comes to fluid shift and cardiovascular deconditioning, those would be also quite interesting results, because I think the fluid shift will have a major impact, more than the body composition, but it remains to be seen.
Okay, another question that I want to ask, because now we are preparing for Moon and Mars, I wanted to ask if tilting could contribute to perform partial gravity bed rest studies, for example, and if other modifications are needed for future bed rest studies to really replicate kind of partial gravity conditions, if we want to address Moon gravity and Mars gravity, and if that is even necessary.
So it's a question to how to simulate life in Moon. So I think there is one component that is low gravity, but also I expect that astronauts in the Moon will have some also strong physical activity. So what is the best way to simulate the Moon? Low gravity is one part, but we should also consider all the activity they should do, and probably long duration of head-up tilt test is not the best way to simulate what will happen on the Moon. So it can be one time, but also we should simulate their activity with their combination, and probably they will be very active and not inactive as astronauts in the space station. I think it's really two different conditions.
I agree with Marc-Antoine. So it will, the tilting will be simulate especially the cardiovascular effect and also a part of inactivity effect, but astronauts will have activity on the Moon. So remember, we made an experiment on this 20 years ago in which we organized head-on bed rest followed by head-up tilting of about 10 degrees, and again, head-on bed rest to simulate lunar gravity. And we did not see many effect on orthostatic tolerance.
Okay, thank you. I think I will now give the room for any questions in the audience. Are there any questions? Yes, please go ahead.
Hi, Anne McCardle from University of Liverpool, UK. I think that was an important point earlier on about the ability to recondition the astronauts when they come back. From a muscle point of view, it's really critical that we know whether they lose complete fibers, because they will never come back. And that leads on to my question really about the plyometric intervention. Is it a damaging intervention? And so if we have a mimic of old age, where there are some indices that suggest that in space, old muscles subjected to an active lengthening contraction won't come back. So do you have any feelings about that, any thoughts about that?
Well, my strongest feeling is that reambulation is the most muscle damaging intervention I've seen. So when people stand up after bed rest, you never see a stronger muscle soreness than that. Mm-hmm. And have the two successful countermeasures that we have had in our labs done anything against that muscle soreness? On the data that we have, creatine kinase, no, we don't have biopsy material, unfortunately. Subjectively, you know, when I talk to people, I would say the countermeasures that we used actually did no good. Yeah. Yeah. So was the plyometric exercise damaging? both the vibration as well as the jumping sledge was associated with some problems of the back in some people. One has to acknowledge. Nothing comes without a risk. It was possible in these studies to accommodate the training paradigm so that people could continue. There was no complete dropout, but it was a difficulty. So of course, it's something that is more risky. We know this from sports also. But if you want to have the full effectiveness, I think it's a very good means.
Okay. So, I mean, it would be interesting to know if the effect on the fibres, certainly on fibre size as well as functional loss.
That's all published. That's all published. Fibre size is maintained. Fibre numbers, obviously, we don't know.
You don't know.
I'm not sure whether I totally agree that fibres that you once lose will never come back. I'm not entirely sure. But anyway.
Okay, we can chat later.
Hello, Thomas Bote from the Charité in Berlin. Very interesting, very diverse talks. I have one observation, and you've all showed comparisons between groups, men and women, countermeasures against control, and that's all fine from a scientific perspective. It's good that you do that. Now, thinking a bit more operationally, we send single astronauts, right? We don't send all men. We just send some men. And now, in all of your data, what I could see is that the difference within the groups is always bigger than the difference between the groups. And you always have some outliers who have very favorable results, maybe in the control group or in the active groups. So now my question to all of you would be, are there some things, some common denominators between all those people, or those very few people, who have very favorable results that could maybe predict who has a beneficial outcome or has an unbeneficial outcome? Because that could be really, really helpful for astronaut selection in the future.
Yeah, in the Vivaldi program, because we will have most of the data that will be handled by the same group, and we will have a different condition. It is one of our goal, just to identify some outliners and see why are they different and what's explaining that, and if there are some correlation between different changes. So we would like to have this more individual approach, and I think in the future it will be very important to have this more individualization in the approach of countermeasure or what we expect as the deconditioning in astronauts.
So with all due respect, I have to disagree in that the responses that we see where they're significant, they are actually smaller within the group than between the groups. That's easy to say because we have only 8 or 10 or 11 subjects. And if you have one effect size, then you require with alpha 5% and beta 80%, you require 13 subjects. So by definition, all the significant changes that you have seen, the between group effects or sizes were greater than within groups. Maybe you misunderstood from some slides that the measures that we take at baseline, their people vary widely. But then when we look at the percent responses to the bed rest, and of course bone is much more variable than muscle. Muscle is really not so variable. It's really homogeneous between people.
I'd like to add that, I would like to support Bjorn's point, and what you are asking is, again, what type of biomarkers we can use to predict a physiological system change to an intervention, right? Actually, Bjorn and myself have a couple of papers published in individual variability to bed rest. In our case, we found actual individual variability because that's something you can't compare like a standard deviations to indicate whether there is actually like real individual variability. You have to follow certain procedures. So following this, we found individual variability, and we checked for the what's driving the individual variability. So then we found that it was height and weight. So there was a regression to the mean, that it happens in all the physiological systems. When something changes, it tends to go back to normal. So it's very difficult to have this, holy grail. Let's look for something that will, But we are working on that. We don't despair. We are researchers. We are stubborn. But it's very difficult. But if some of us gets the solution, that will be a total game changer.
Okay, we have time for one more question. Please.
Yes, Dieter Blottner from the Charité in Berlin. I have two comments to make related to the dry immersion. 3 days, 5 days, or 10 days related to muscle. I would say that related to bone, this does not make a big, let's say, change, but with a muscle, I would guess, we have seen muscles from 5 days dry immersion. There would be a big difference, also related not only to the ultrastructure, but also to things like tone and stiffness. So I would very much talk in favor of increasing the time to 10 days, what you suggested. So this would be really give, let's say, an additional effect on this particular protocol. That's just my idea. The second one, I mean, we have seen many of the muscle biopsies. Jörn and Uli, where's Uli? We were the people who did the biopsies, and I looked at them. Related to the question from someone from the UK, I guess, was it? You, thank you. I would say we haven't seen much of any histology changes, but if you go to ultrastructure, you see a lot of changes. For example, vibration or the plyometric training, the sarcomeres, they disrupted. They are disrupted. But the main question is this really a problem, or is this just what you see in sports, or what you see if you're on athletic? So I would guess this is just a training effect, and what happens in ultrastructure does not really affect, the things. If you go to histology, if you go to gross anatomy, then changes or injuries may have an impact, but not at the ultrastructure, I would guess, because muscle is an adaptive tissue, and I mean there is a readaptation, so I would not see any big problems.
Sorry, just to interrupt. I think the point.
Please, we are in a discussion.
I was maybe not clear. So if you did that in old age, it would be a problem. What I was wondering was whether on the ISS or in microgravity, if you do that there, it behaves more like old age.
In old age.
So that was yeah. So the younger people will recover.
Yeah.
I was just a little. My question was actually a study in older people would be quite interesting.
Okay, but the astronauts are not old people, so I would say the muscle sometimes, but not always.
Yeah.
Not always. Okay, so just my comments. Thank you very much.
Thank you. Well, I would like to thank the speakers for being here in the panel, and thank you everyone for being in the audience. We are a bit over time. It's now time for the lunch, but we adjourn in the afternoon, so see you later. Thank you.